this video, we are going to show the concurrent real-time FPGA workbench lvdt rvdt IP module. LVDT stands for Linear Variable Differential Transformer, and RVDT is Rotary Variable Differential Transformer. From a mathematical perspective, the LVDT uses distance or the core location as information into an amplitude modulator. So we can see on the left-hand side a circuit diagram of the LVDT. We can see as the core moves, the excitation signal across the primary winding is applied across the two secondary windings. In the FPGA demo, we will use an external signal generator for the excitation. The four plots starting at the top, the first is the LVDT normalized input distance from the center. The next plot is VS2, the voltage across the top secondary winding. The next is VS1, the voltage across the bottom secondary winding. And the final plot is VD, the difference between VS2 and VS1. Now let's look at the hardware, software, input, output, and controls to our FPGA IP module. The inputs to the LVDT module are the normalized distance and the excitation signal. These can be controlled via our SDK, programming FPGA registers, or can be controlled by analog signals external to the FPGA. The outputs to our LVDT RVDT module shown here are VS1 and VS2. These are those secondary voltages across those secondary coils. But the FPGA module itself has many different options for outputs. Lastly, the control parameters allow you to switch between LVDT RVDT mode. They allow you to switch between internal and external excitation. And they also allow you to switch between software programmed distance of the core location or external into an ADC. Lastly, we offer a fixed functionality FPGA board that comes with 8 LVDTs on it. Additionally, it comes with a transformer coupling card. This card has a transformer coupling the external excitation inputs and 16 transformers coupling VS1s and VS2s to the output. Now finally, all of our FPGA IP modules are integrated into Simulation Workbench. Simulation Workbench is a comprehensive framework for developing and executing real-time hardware-in-the-loop and man-in-the-loop simulations. And these are two screens showing how LVDT is easily used in our Simulation Workbench tool. Now we're going to jump into the Linux box and we're going to show the demo. But before we show the demo, we're first going to show FPGA Workbench. So if you want additional information on FPGA Workbench, please see some of our other videos, or please inquire about the documentation. In the canvas, you see we have 8 LVDTs, RVDTs, which are these modules in the middle here. And then we also have 8 analog inputs, A0 through A7, AI through A7. And then we also have 16 analog outputs, 0 through 15. Now this code has been burned to our FPGA board, and we're going to show a demo moving the core and changing the excitation signal. So let me now switch over to the oscilloscope and some of the SDK and some of the readback registers. Okay, so what we have here in the top left, we have a window showing our SDK. The SDK allows us to easily control all of those parameters that we previously showed on the block diagram. Beneath it is the readback registers. Each one of these rows represents an LVDT module, and each column shows some readback information from that module. A couple of the ones of interest, 08 will be the normalized distance in a 2's complement format. 0C and 10 are VS2 and VS1, and 14 is the excitation signal. On the oscilloscope, we have a yellow signal, which will be the excitation, and the green will be VS2, and the blue will be VS1. So now let's start controlling it. Let me leave that up. And so now first, we are going to turn on the external excitation. Okay, so we have the core in the middle, and the blue and the green signal are equal, and we can see the excitation signal around 20 volts and at around 8 kilohertz. So now we're going to slowly step the core up. So we're going to move it to 0.5. When we move it to 0.5, VS2 increases, and VS1 gets a little smaller. Now we will move it to the max positive distance. And we see the green signal is at maximum voltage, and we see the blue signal is at minimum. Now we'll flip it so that the core is all the way at the bottom. We'll continue on moving the core up to minus 0.5. And then we will move the core back to the middle. One more time. We see the signals are equal, and we'll slightly offset it for the final tests. Okay, so we see that we can move the core around, and now we're going to do one last thing. We will make a change to the excitation frequency. We'll move it to 4 kilohertz. And lastly, we can also change the extra excitation signal voltage. Okay, so with that, concludes the demonstration of our lvdt rvdt module. Thank you very much for your time and your interest in our concurrent real-time FPGA and our lvdt rvdt module.